distinguished professor since 2006 in the Department of Physics, University of Florida. She has numerous awards and appointments and fellowships and honors. So I wouldn't even try to list them. She has published close to 300 papers, has close to 10,000 citations. She's fluent in several languages, almost six languages. So it's a long list. She's a fellow of American Physical Society, and she has been productive all these years. I mean, she still is very active, not just publishing and getting funding. From 2007 to 2016, in 9 years, she has secured more than $7 million in external funding. So that is a testimony of her achievement. She is very active internationally. She travels a lot, collaborations and giving talks and advising and all that. So it's truly an honor to introduce her and have her as the first speaker of the workshop. Her title is going to be Polypeptide Structures on Metal Surfaces: Insight from Theory. So with that, I'm happy to let her tell about her recent work.
Thank you so much, Ghanim. You really, I'm almost embarrassed with all the things that you were saying there. So I hope I can live up to some expectation here. And it's a tough job because when I looked at the schedule, it's on nanomaterials, which I felt very comfortable about. But then when I looked at the titles of the talks, they were mostly on biophysics. So I chose one topic in which the subject is close to biology. But then, and so I'll tell you a little bit about what we have done. Probably this is the closest that I have gotten to biology, and then I'll switch over to talk a little bit about another system that's of a lot of interest to what I've been doing. So as Ghanim mentioned, my background is in surface physics. So a lot of what I do is related to surfaces. Of course, that has lent itself into going into nanoscience because, that is basically the groundwork for nanoscience was laid by all the techniques that were developed because of surface science, STM being one of them, but not the only one. So it's you will see that what I'm talking about has hints of that. So first, let me do a little bit here about polypeptide structures on metal surfaces. I also should say that it is always a pleasure to be talking to a Pakistani audience, and here it's even more of a pleasure because it's a subcontinental audience. So that's really something that's very close to my heart. I go to Pakistan very frequently, and we have been organizing workshops in Pakistan on a regular basis. And so I think some of the people who are signing or getting ready to sign on, because it is still early in the morning in Pakistan. I hope there's some familiar faces there. So what I'll do today is that these polypeptides that we did, the work that we did, it was really because of Stefan Rauschenbach, who is now at Oxford, professor there. And this is during my visits to Stuttgart, where I go pretty often. He taught me and my collaborator, that's Dewey, who's he did his PhD in my group and then has been with me for a while. He got us interested in looking at these structures, and so we said, okay, we will apply some of the techniques that we use on surfaces to look at the system. Before I go to that, I should just point out to where I am, and Ghanim already mentioned. So this is Orlando. Ghanim is over here. That's Tampa, and that is not too far away from us. and these are both very large universities. UCF is I think the largest university these days in the country, over 70,000 students. Of course, we have had a lockdown, so we haven't seen any of the students for a while. But anyway, there's quite a bit that goes on. It's a relatively new university, just like USF. These are both relatively new universities, but they are in an exciting area of the country, and so lots of young people like to be in Florida, and so these universities are huge. All Florida universities are huge. Okay, so I should give credit where it is due. I mentioned already that Stefan is the one who really got us working in this topic. And these are all these are members of Klaus Kern's group at Stuttgart, and Du is the one who works with me, and Michael Dürr and Ludger Harnau. They were the ones who did the molecular dynamics simulation. Particularly Ludger Harnau did some very difficult molecular dynamic simulations for the system. So what is it that is exciting? I think the main part of this talk is really, it is more the experimental, feat that they had in imaging these molecules. So imaging is of course quite a difficult task as such, but to make these molecules land on a metal surface so that they can be imaged, and it's really very challenging, and there are not that many groups in the world that can do that. And Stefan had in Klaus Kern's group, which is a very large group at Stuttgart, Stefan had developed this technique, which is this electrospray ion beam deposition. So essentially you're spraying these molecules very softly onto the surface and hoping that they don't break before they land. And once they land, you hope that they will stay long enough so you can image them. And of course, as you know from STM imaging, we can get a lot of information about their geometric and electronic structure. And so that was the reason for doing that. Of course, there are other reasons too, but which I'll go to in a minute. But what you see here is that there's certainly some interesting features that are being seen, and I'll show you the differences that they observed, and when they did it on either copper 111 surface, which is this hexagonal surface, or this surface, which is rectangular, and then another 110, which I'll show in a minute, where they get even different result. So the question is that what is the surface doing to it, and what can we learn about these peptides if we can image them? So part of the thing about imaging is that unlike techniques like XPS or photoemission or vibrational spectroscopy or others, there's a lot that goes in interpretation, because of course what you will see will be structures, but then what are these structures? It is, what is the chemical composition here? What exactly is going on? Because what STM is doing is basically mapping out the charge density, right? So if you, I have another picture, I guess the next slide will show you that essentially what the rationale for this is that if you're looking at STM, then STM essentially you have a tip, and then you have the structure that will be the surface, and then on that will be the sample there, and then essentially you're going to be either controlling the current or controlling the height of the tip. And typically you really do it with the in a not a constant height mode, but a constant current mode. But what the tip is sensitive to is the tunneling of the electrons. So the tip will be, so there you see it, that's the tip, and that's your surface. And the tip is quite sharp. In fact, there is some effect of the geometry of the tip on the measurements that are taken. but not so much that you you don't get information about that you need to know exactly the structure of the tip, although it will be good to do that. So basically, what happens is that it is the quantum mechanical event tunneling that we are always looking for, which is what makes the difference between quantum statistics and classical statistics, is that essentially you have a metal here. This is typically it's tungsten, or it gets coated, of course, with whatever it is measuring. Regardless, it is a metallic tip, and depending on the bias that you provide it, it can either be picking up electrons can tunnel to it or tunnel from it to the surface. And so the surface also has to have some kind of a metallic nature to it, otherwise you won't be able to do tunneling. So that's the difference between STM and AFM. So basically, what this does then is that you move the tip, and as the tip moves, depending on the charge density that is underneath it, that it experiences, the current or the tunneling current will be proportional to the charge density. So that is the main thing behind it. And so if you use this measurement, you like you saw in the last picture there, what you're really seeing is that there are some regions that have more electron density than the others, and then of course there is the substrate underneath, which they're not imaging because they're further away from it. So a lot of information comes in, but it relies a lot on theory to sort of get the full picture. And so that's where we come in, and that's where we've been working with several groups that do this kind of work. But the thing about folding of a protein, of course, is important for other reasons too. I mean, of course, folding is by itself a major theme, and and the question here is that if you could fold proteins, and if you could do it in a controlled manner, then you could get you could really get a robust self-assembly. And since proteins and peptides and so on, and when we're talking about nanomaterials, we know that these are very functional materials. They have all kinds of activities that they could be employed for. And so having a controlled and robust way of obtaining these things self-assembled on surfaces, right? I mean, that's one of the things that we do on surfaces is you get organic films to self-assemble, and then you get functionalities like just your screen right here on your computer. Those are all examples of organic molecules assembling together to produce the kind of device or functionality that you want. So the challenge, of course, is how are you going to do it? And that's where Stefan's electrospray came into effect here. The other is that if we do it on the surface, which is what these guys have done, you have eliminated the effect of solvent. So part of what goes on when you are thinking about protein folding in the normal way is that it is in a solvent, and so the solvent plays a major role. The question is, what happens when the solvent is not there, and could there be some other information that could be obtained, and also could the surface itself facilitate certain properties of these proteins? So that's what got us going. Let us see why I'm stuck here. Okay, there it is. So that is, and I will not tell you about the experimental details, except to show you some results. But basically, what the challenge here was that these are very large systems. So you're talking about hundreds of atoms, or close to 1,000 atoms, and or more actually. And so then the question is, how do you do these kinds of calculations that I do, which are based on density functional theory, which I'm not going to talk about here, but essentially what density functional theory is that we cannot solve the Schrodinger equation for any system. You know that the only system for which we have solutions is the hydrogen atom. And of course, we have not just hydrogen, but many other atoms in here. So obviously, we cannot solve Schrodinger equation. And so physicists and chemists have devised various ways of approaching the problem. And we do like a pseudo Schrodinger equation in the sense that we basically look at an equation that has the Hamiltonian, that has the makings of what would be a Schrodinger equation, but that we consider the properties of of a single electron in an effective field of all other electrons. So it is a simplification, but it is a technique that has had quite a bit of success. For various reasons, it has worked out. So basically, what we have done here is density functional theory-based calculations. And if you have questions, I can give you more details of that. For now, I think it would be best for me to just tell you that that's the technique. It's a standard technique. There are lots of codes that are available. I have also been involved in development of some of these codes, but they are certainly available now very freely. So the thing is that we rely on classical molecular dynamics simulation, which a number of people in audience know about, and essentially for classical molecular dynamics, you need to know what are the potentials between all these atoms that are in this system. So this is also non-trivial. My colleagues in Germany who did these classical molecular dynamics simulations spent a lot of time using a code called GROMACS, and then also testing out all kinds of two-body and three-body interactions that would give you semblance of some kind of appropriateness to the system that we have at hand, which is a rather complex molecule. Okay, so these are the techniques that are being used. So essentially what they did in the MD simulations is they focused very much on the molecule and its interaction with the copper substrate. They kept the substrate frozen in the simulation. So that is, of course, an approximation. But they were mostly interested in predicting some of the structures of these molecules, which we could then use as the starting point in the density functional theory calculations. And then once we did the DFT calculations, then of course we could get the charge densities, the charge density distribution in the entire region of the system. And the system, of course, is not just the molecule. Molecule itself would have been challenging enough, but what we have to deal with is also a molecule on a surface. So we have to consider a system containing several layers of copper atoms, and so that makes it very, very time consuming. But once you've done those calculations, so once you know the structure, or at least a starting structure, which is reasonable, then actually things can be pushed forward. And once you get those, then you can calculate STM images so that you can make comparison with experiments. And of course, you can do an analysis of the electronic structure and so on, which is what you will see. So when the MD simulations and as some of the structure was already known. I mean, just we know what the constituent 9 amino acids are. That's what this is made up of. And so these were the structures that came out of MD simulation. So there were some that resemble these. These are individual molecules, and these are some that are combinations of the two form. Okay, so back to what was being done experimentally. I wanted to show you here so that we, those of you who are working with peptides probably have better idea than I do. But what is particular about this is that it has what they call the C-terminal, and that is actually a rather well defined and has a beta turn motif here. But if you look at this other terminal, which is they call the N terminal, that actually can go in various directions. So it's quite a bit of randomness over here, and that also was one question about how can we classify the system. So the other thing that is that so these are the 9 amino acids that are involved here. Now, what they found is that when they did the electrospray, that actually for the molecules that got absorbed on the surface, they got this really good validation. And so this was the molecule that has a charge of +2 is the one that is stable on the surface, and they can, pretty much swear that they actually have deposited the molecule intact because of the confirmation from the mass spectrometer. Okay, and the other thing is that this is one that a singly protonated molecule was detected after soft landing. So this is the one that was there before the landing, and this is after the landing. So that gave them good bit of confidence in what they have. But here is what was interesting in what they found. What they found here is that these are the individual molecules. So when they did the measurement on copper 110 and also 111, I showed you the 111 picture right at the beginning. What they saw, and these are again what's coming from MD simulations. So they see these types of configurations. If they go and look at or the sample, what they find is that about 40% of the sample has this configuration, has the A configuration. And about 30% of them have this B configuration. These are single molecules, okay? And every now and then they come up with this configuration, which seems to be a combination of these two. So that's what we think. And then there are some that look strange, that we have not been able to classify. So we can't say that we understand every image that they see. However, when we do STM imaging, we do find a number of them which would have this structure or even a combination of this. But these are still single molecules mostly, and that is on the 111 surface. And similarly on the, this is the 110. The surface that is different is the 100 surface. And so what happens on the 100 surface is that you are not seeing, and if you see those images, they're quite different, right? Here they're looking quite haphazard, doing their own thing, and resembling the kinds of patterns that we would predict from MD and then with DFT. But when you look at these, then the conclusion that we came to, and again, you see that they're almost like split, there is you can essentially have a reflection plane here, more or less, and structures like this. So what we found is that these were all structures that told us that they were dimers. Okay, and so that is what the analysis led to, is the fact that you could have dimers in several configurations. So one of the things that came about is that copper 100, there's something about this surface that is affecting that is promoting the formation of dimers. So only monomers on the other surfaces and dimers on the 100 surface. So that is the conclusion that we got to. So what is the difference between them? I should also tell you that in all of these, what was found is that, and again, the scale is 1 nanometer. So you're seeing something like 3 nanometers this way. And in the case of 100 surface, it was also about 3 nanometers that way, right? So that was almost a square. Let me just go back here, because what I should mention is that, again, they see, and in this case, they would see something, again, that's 2 nanometers. So seeing about 3 nanometers this way, and about 1.5 to 2 nanometers this way. So the other is that you would ask how high are they above the surface. So actually the protrusion was very small, and just an angstrom, between an angstrom to less than 2 angstroms. So the protrusion was really small. So that makes the image that we have is that these are really flat discs that are on the surface there. So why does it form dimer on this case? So we went to look into this and say, well, what could possibly be happening? So essentially, we are all the time when we're doing, there's a lot to be juggled here, because it is such a complex system that you just don't have all the information that you can get from experiments. So we're always comparing what we get. We take a model that looks reasonable, and then calculate the image that should be seen in STM. So these are all calculated images, and then we look at pictures like this here, and then see what is the comparison. So what we found is that the first two were not as prevalent, but this one was one that was being seen in several of these cases. Okay, so we would argue that this is probably the best scenario, although one could rule out this one also. This one didn't see, so this one could be ruled out, but not these two. So this was what we proposed, and the question is, what's going on? So if you look at it, so here we're looking on the 100 surface, and the other thing is that these are being held on the surface mostly with van der Waals interactions. Okay, so it is really weak interactions. You don't have much of a bond formation except the following. So in our experience with working on surfaces, what we find is that if you have something that is about 3 angstroms or more away from the surface, then that bond is never covalent or ionic. That bond is what we would classify as a van der Waals, or basically a Fizeau system. On the other hand, what you find on 100 and not on 111 surface, that what we find is that there are so these are copper atoms which are close to nitrogen or oxygen atoms. And so there is some bond being formed between the nitrogen and oxygen atom of the polypeptide and some copper atoms. And so what you have here is these are here. So what our argument here is that these bonds, these green ones that you saw between copper and nitrogen and oxygen atoms, and then these hydrogen bonds that go on over here, that these are the ones that keep the this peptide folded. I'll give you another reason, more convincing reason in a minute. But then what we have here is that when we look at that structure, so we would say, okay, this looks like a pretty fine structure, which seems pretty reasonable. So now when we go and we look at this structure, then we find something interesting. In fact, this would be the better. This is just telling you where the carbon and the nitrogen is blue, the carbon is black, and the red is oxygen, and the magenta is hydrogen. Okay, so these are where the atoms are, right? But what is interesting is this distribution here. This is what we call the Bader charge analysis. So we've looked at the charge distribution in these different areas. So the green is where there's no charge. So what is interesting is that the way this thing is working out, and what the copper 100 surface, because of its interaction, is doing, is that all the charged or the dipoles that you, if you want to think about, they're all over here. So this here, an orange and a blue, that is certainly a dipole, right? Because you've got negative charges here, positive charges there. So lots of these positive, negative charges or dipoles that are here, but all the polar components are actually inside and not outside, and which is the opposite of what happens to proteins in solutions, because they're the unprotected ones, I mean, the unpolarized ones are inside and the polarized ones are outside. Part of the reason is also because they're in a solvent, so they certainly, the charged parts interact with the solvent, but there is no solvent here, and basically what the protein is doing is folding here, dimerizing here into these structures, so that it actually becomes immune to interactions from other neighboring structures. We in the images, they hardly saw when monomers were moving around and dimers, these things do have certain diffusion on the surfaces, but monomers more than dimers, of course. But you hardly ever find monomers surrounding these dimers. So somehow this structure. So that was basically our argument, that essentially these things are dimerizing because of this folding that is going on. So what happens on the 111 surface? Well, we did very similar structures. We tried to get a comparison with images. Those are the images that you're seeing in experiments. These are some of the calculated images corresponding to these types of structures. There's not always 100% agreement with these, but one of the things that we did find is that there is, when we are on the 111 surface, then what you see is that there are few copper atoms that move upwards, and only a few copper atoms that are at a distance less than 2.5 angstroms. We had many more. If you remember from the picture that I showed you here, there were far more than in the picture that we have here. So basically, our conclusion from here is that on the 111 surface, it is not so strongly bounded, and so then the dimers don't really come together. So the surface helps bring the atoms together on the 100, and so they dimerize. And once they come together, it's really the interaction between, within the molecule, that gives them the configuration that we see. So basically, my conclusion here is essentially that, yes, we have done these calculations, and we find that, in fact, some of them, these structures like this one over here, is the one on the 100 that gives a pretty good agreement with experiments. And the explanation that we find is that in all of these structures which are stable, the neutral parts sort of hounds or essentially forms a boundary along the polar parts, protecting the polar parts from interacting with other species on the surface. So this is basically my summary of the first part. And I see that I've taken more than the time I thought I would take. So I don't know, Ghanim, do I have a few minutes to go over this, or what do you think?
Yeah, I mean, you could go for another maybe 4 or 5 minutes.
4 or 5 minutes. Okay, so let me just be quick here. And there are quite a few talks going to be given on 2D materials. So I thought I will motivate it by looking at some of the 2D materials that we have been looking at. We have been looking at molybdenum disulfide very extensively, but lately we've been very fascinated with this material. This is just a single layer of boron and nitrogen and this is like graphene, except that you have two elements, boron and nitrogen. And the main point here is that if you had just a sheet of boron and nitrogen, or sheet of hexagonal boron nitride, that has a really large band gap, and that's not the one that is going to do have any catalytic properties. But with the vacancies, it will. This is just a group of people that I work with, but I'll come back to that later. Let me just say that what I wanted to show you here is that what we tried to address, and I'll just give you a few slides on that, is that you have carbon dioxide, that is an eternal problem, right? If we have far more carbon dioxide than we can handle. Of course, carbon dioxide, if you left it for millions of years, then it will essentially be converted into oil by nature, but we can't wait for 1 million years. So essentially, there are all kinds of ways people are finding to capture carbon dioxide and to convert it into value-added chemicals, right? So 2D materials are of course a good playground. One of the things is that they have a large surface to volume ratio, They are in fact all surface, and so a lot of things can be done there. But the problem with 2D materials is that they are inert, and that is where defects come in. That if you didn't have defects, then basically they are, let me go over there. Oh, okay. This is, yeah, right. So basically, if you don't have defects, then you are going to have a large band gap. And I'll show you that in a minute. So we basically looked at 4 types of defects here. Either a boron could be missing, or a nitrogen could be missing, or you could have a boron in place of a nitrogen, an extra boron in the system, or you could have some kind of rotation of bonds, which is called stone whales, okay? The main issue is that uh, is, and here again, this is more physics than biology. So you have this large band gap here, and if you didn't have the defect, then these states would not have been there. But the presence of these states very close to the Fermi level is what is causing these materials to be reactive. And another way to think about it is that when you have this band gap, then essentially you have this electron cloud. So that the charge distribution, and I mean, when you have a vacancy, you have a charge distribution around that point. And so what does that do? So here is what I will show you, and then I will basically come to my last slide. Uh, so the question is, could the defect state, so this is my defect state. I have removed a nitrogen, and that's the one that is most plausible. And now the question is that because I have a nitrogen vacancy, obviously then I have charge redistribution. Could this activate CO2? Activate meaning capture it, and then could we proceed for a reaction? The answer, of course, is yes. So how does it go? So if you look at it here, we've got carbon dioxide. These are not the atoms. These are the orbitals of carbon dioxide. Okay. So particular orbitals, this is what we would call a frontier orbital, orbitals that are very close to the Fermi level, as physicists always like to think about, and or orbitals that are foremost, let's say, ready to interact with something. So as it comes, so basically, if you keep your eye here, you know this is coming coming closer to the surface, and what you really should see is how this picture over here is showing you how the carbon and the oxygen are going to get engulfed in this charge distribution that is there because of the vacancy. So as you see, as you come up, it is getting wrapped up in the charge density distribution, and basically much and more totally engulfed in it until finally it is totally absorbed and sitting on the surface. What is very interesting about it is that when it is now sitting at the surface, not at the vacancy, but at the rim of the vacancy, there's still a charge distribution over here. And what we will argue is that that actually is going to facilitate now a hydrogen to come and get absorbed there. And so what will happen here? So this is your hydrogen, and it's coming close to the surface. So a very similar picture. And you can see here, that's the carbon dioxide. It's sitting on the surface, and now comes the hydrogen. And you see the hydrogen on the left part of my screen, right? And so there it is, and on the right side of the screen. And then it comes in, it comes closer, closer, closer. It comes, and eventually the bond between the two hydrogen breaks, and it sits there dissociated. So basically, what has happened, you had the vacancy. The vacancy introduces a charge polarization in the area. It helps capture carbon dioxide, and it helps break the bond of an incoming hydrogen. So once that bond of hydrogen has broken, of course, the process can start. And so this is just to show, I was showing you hydrogen and carbon dioxide. We've also done work with the other ethene and propene and so on, and found that this is actually surface is pretty reactive. Okay, so this is basically the step that I showed you, But let me show you one more step here. And this is basically showing you that, you have the carbon dioxide and the 2 hydrogen, and now you can get this complex here. This is a very important one, because after that, when 2 more hydrogen come, you're going to get formic acid. And so you will basically, this would have shown you how to get formic acid. I won't get into that. Let me skip all of this and to show you this thing over here, which will take me 1 minute. Okay, so this is what I've shown you so far, that you can get both the carbon dioxide and hydrogen there. And then showed you, I didn't get into the details here, but there's an order in which these molecules should co-adsorb. But regardless, they will adsorb, they will form formic acid. And then you will say, of course, what you're going to get is formic acid. But actually what we find is that that's not really true. You can get formic acid, but there is another path, particularly if there's some water present in the system. And if you were to go through all of this, which I won't bother you with, you will actually get methanol. So we did this prediction because before there was any experiment done, and my colleagues, and I'm going to skip all of this, and when my colleagues did the experiment, and this was a ball milling experiment, what they found is that at lower temperatures, like 20 degrees centigrade, they do get methanol. They actually found that at higher temperatures, you can get formic acid, but then they get other products too, which is a problem when you're doing things at higher temperatures. So I think I will just close this part, which was very quick, but I thought you would be interested. And we have a publication already on this, that this particular material can give you methanol. Okay, I think that's it. Thank you very much for your attention. So I will
Thank
stop
you.
sharing and see if you have any questions.
Okay, so thank you for a very interesting talk. And now we will move on to questions. If anyone has any question, you can raise your hand or type your question.
And if you don't have questions, you can send me questions later.
Ata has a question. Ata,
Yeah.
go ahead. You can ask your question.
Talat, it was such a nice talk to listen to. Regarding this kind of reconstruction of the polypeptide on the copper, can we think of a platform which one can kind of electrically control, perhaps, such that you're able to control
Right.
this phenomenon
Yeah,
of
yeah.
reconstruction itself? Yes.
Right, right. So
So
and that is exactly what that charge distribution is telling you, right?
yes, yes.
Yeah. So yes, I think that would be very interesting, and that was part of what they were thinking about in the STM as well.
Mm-hmm.
But there is so I think what you're thinking about is that you go with some kind of a bias, right? And
Yes.
then see if that can. Yeah, I think that is possible. I'm not sure experimentally how easy it is.
mm-hmm.
That's mainly the problem,
Okay. Yeah.
right?
Yeah.
But on the other hand, at those days we were not thinking in terms of putting these molecules on graphene and so on. But graphene would be a very good one,
Mm-hmm.
because you could put it on graphene.
Yes.
Graphene has some electrons, right?
Mm-hmm.
And it won't bind to it very strongly, and graphene can obviously be gated. So yes,
Yeah.
I think that
Yeah.
is certainly very much a possibility. We did this work, about 5-6 years ago, and then Stefan moved to Oxford, and we haven't followed up. But it would be very interesting to get back into it.
Okay. Yeah. Yeah. That's what I was
Yeah.
thinking along the lines
Yeah,
of
it actually could be
two-dimensional
quite
materials.
interesting. Yep.
Yes.
Yep.
Yeah.
Yep.
Thank you.
Yeah.
Thank you.
Yeah, I think particularly because of the polarity that it shows. Yeah.
Yes.
Yeah.
Yes. Yes.
Yeah.
Yeah. Thank you.
No problem.
Any other questions?
Sriram here. I had a general question. First, I wanted to greet Talat. I now realize we've met many times at March meetings, right?
That we
So
have,
made the
of course
yes,
we have. Yes. So where
Just
are
not
you
connected
right now, Sriram?
Bangalore.
Yes.
Yeah, Institute of Science. Many
Yes.
years now, 35 years.
Yeah.
Yeah. No, my question was about your sort of taking a protein and placing it on a metal substrate. The point is that that problem becomes, in some sense, completely different from the protein in solvent, right? I mean, the folding or not folding or the willingness to fold depends entirely on the ionic environment, on the.
That's right.
Right. So I guess the point is just that you can define a new polymer sort of collapse or otherwise phase diagram for each substrate that you place the protein on, I guess you would say, right? Yeah.
Right. So
Okay.
I think what the interesting thing that came out of it is, first of all, in the what you're seeing about folding is almost all of it is controlled by the solvent, right? I mean, without the solvent, it won't. So then the question is, if you don't have the solvent, then would it do it? So we saw that on some it doesn't, but on others, right? So basically, what the solvent also does, but what I find fascinating is that in the solvent, because the solvent is usually ionic, you would see the polarized parts outward, so the structure would be different. But now the question is, and Ata's question is a good one, is that now that you have it this way, could it be controlled electrically? That actually is a very, very interesting idea.
Right.
Yeah.
Okay, thanks.
So, well, if I'll try to sneak in tomorrow. Tomorrow is what? I don't know. I'm lost right now. It's 1:45 for me.
Yeah. So it's my talk is this afternoon at a completely impossible time for you. Don't worry.
Okay. Well, hopefully we'll catch up with you sometime.
Right.
And yeah, my regards to Chandan if you see him.
Sure.
Okay.
Talat, we would have his talk on YouTube. So I mean, you can watch it later as well if you want.
All right. Yeah. Okay. Well, thank you very much. I'm sorry that I can't stay for most of the talks because.
That's okay. Thank you so much. I guess in the interest of time, we will move on to the.
Thank you so much.
Take care. Bye-bye. So our next speaker